Okay, so let's hear Jeongwan Haah talk about lattice codes.
Thank you for giving me this opportunity to speak here. I am going to present about some formalism and my point of view towards the lattice quantum codes. It is really intimately related to the previous talk by Vishwanath. It's deeply related to gap spaces, how to understand them, and what phases are there, especially in higher dimensions, not restricted to 2 dimensions. And this is a very this leads to an example of very counterintuitive nature, where the previous notions of the topological order, where the topological order is not really defined, but it's characterized by a set of properties. For instance, ground state degeneracy depending on the lattice topology, and the topological entanglement entropy, and those properties that do not really survive. I mean, they do not really depend on one another. And I will try to be rigorous, what implies what, and what can go wrong, and what remains true. So since my example in the end will be very counterintuitive, I will try to be rigorous as possible, although using very simple example of the 3-dimensional Toric code. Let me just first start with I assume that you are not too familiar with the quantum codes in the first place. So let me briefly review what the quantum codes were.
Can you say again, what are the 2 things that you don't want us to think of as the same?
So I will distinguish them, and well, I'll try to be specific as I go. So let's not think about lattice for a moment, and let me just define the word, the quantum codes. What is the code? Well, it's not something complicated. It's just the subspace of some many qubits. That's it. Of course, it's not an arbitrary subspace. It has to be cleverly chosen so that it gives some property of error correction. But I'm not going to talk about error correction at this time. In one particular and most important class of quantum codes is called stabilizer code. Or some mathematicians would like to call it additive code. But this terminology is more popular, although I like this one better. This is a subspace of many qubit Hilbert space that is +1 eigenspace common. It is defined by the +1 eigenvalue subspace of a commuting set of Pauli operators. By Pauli operators, I mean tensor products of Pauli matrices. Each Pauli matrix is acting on one single qubit. Well, let me give you an example. Suppose I have 5 qubits. And I suppose I introduce a Pauli matrix tensor since I'm going to talk about only for Pauli operators in this talk, I will drop the sigma simply and just play with the x and z's. Just notation. given those 4 operators, we can simply check that each of them is commuting with one another. Because if I multiply in this direction, then I will have z and x. But, oops. Oh. The anti-commuting pair of Pauli matrices always come in as even numbers, so they always commute. So we can think of a common eigenspace of those operators, and we are left with some subspace that is not non-trivial. And the operators that act on that common eigenspace can be chosen to be a Pauli operator as well. And in this particular case, they can be chosen in this way. You can check that each operator commutes with every one of 4 operators, and themselves are anti-commuting. Therefore, they act as a non-trivial operator on the code space. This is always true, and I would like you to remember this fact. For any stabilizer code, there exists a Pauli operator that can generate the operator algebra on the code space. So in order to learn the operator algebra, what's going on to learn on the code space, only you need to study its Pauli operator. That's enough. But so the operator that acts on the code space is called logical operators.
Are you saying they determine the other one? They are just commutative of each other, right?
Commutator of each other.
Well, this logical operator and this stabilizer, they just commutative of each other as algebra inside. So you are saying this one determines the other one?
No. Logical operator alone does not determine the code. Well, a set of all logical operators will determine the code entirely, but a pair of representatives will not. But logical operator can be in a very different form. For instance, if I have some wave vector in the code space that is stabilized by these operators, well, the name stabilizer comes for this reason. Since I'm talking about +1 eigenspace, naturally, if I pick a vector in the code space and apply one of the stabilizers, it will give me +1 eigenvalue, which means it stabilizes that code vector. This state can be written as, say, let me call this S1. It can be written in that way because, well, by definition. But this operator is different from the original X bar. This is although the form is different, the action on the code space is identical. But one thing you would notice is here are some identity operators, which means in order to act on the code space, I don't have to act on all qubits. I have to pick a special subset of qubits, and that will suffice to obtain that action. So this is a brief review of what the stabilizer code is. In terms of coding theory, people are interested in how to pick this set of stabilizers such that among all representative of logical operators, the weight of the number of operators that are not identity to be large as possible. because that is closely related to air cracking power. Now, let's go to, and one thing that is very important in every stabilizer code, the logical operator should act on at least 2 or more qubits, which means if I act on one single qubit, the operation will not be reached into your code space. Even though code space is non-trivial, at least there are 2 or more wave vectors in the code space, they will not be able to distinguish by acting on a single qubit. In other words, if you take the reduced density matrix on a single qubit of any good quantum code, that will give you identical for every code vectors. So any stabilizer code comes with the property of local indistinguishability. This property is actually shared with any topological order system. In the previous talk, Ashwin talked about the Toric code and it depicted the caricature of the wave function where the strings are fluctuating. Since the strings are fluctuating, if you look at the local reduced density matrix, there's no way to tell which state you are in. That is exactly that property. So quantum code is designed to study locally indistinguishable states. So if I imagine some physical system where the ground states, degenerate or not, especially in the degenerate case, if the wave functions of that ground state has a property of local indistinguishability, then we can formally think of it as a quantum code. Although it may not be presented as a stabilizer formalism, but it is some sort of quantum code. So let's get back to let's approach the problem in a reverse direction. Instead of studying quantum code aspect of the real physical system, we just study what phases of matter can be represented using quantum codes, especially the stabilizer code, where the algebra is simple. This is my question that I would like to address in this talk. So let me be more specific to the setting. I imagine a system with a Hamiltonian that is given by sum of Pauli operators that acts on some geometrically local subset of the whole lattice. And I want to restrict myself to the quantum code setting, the stabilizer code, and I want this to be just Pauli operators. I don't want to play with all kinds of Hamiltonian. I want to restrict to this simple setting, which means I am imposing the commutativity condition. And most physical systems are translation invariant. So it doesn't really have to be, but for simplicity, I impose the translation invariance. Now it comes to the question of what kind of lattice should I choose? Ashwin told us that in 3 dimensions there are 230 kinds of lattices. It's a lot. But when I restrict myself to geometry local and I slightly release my condition where the locality means, I just mean that it should act on a small set, not necessarily in the nearest neighbor interaction. But with that relaxation, all lattices are not important. Because when you talk about lattice, all that matter is what lattice points are nearest to another things. So I can simply replace all my lattice with a simple cubic lattice. The price I have to pay is that for each lattice site, I have to allow many qubits. It wouldn't be the case that a single qubit is placed on a site. So of course, because of the translation invariance, the number of qubits per site will be the same at every site. One technical assumption here is that I don't want to be bothered with the frustration. So this is my setting.
Can you remind me, frustration free, you mean if they commute?
A frustration free means that each term is minimized at the ground state. So now let's investigate the very familiar Toric code in detail. And I will develop my own calculation method and replace some small parts of it, and we'll obtain a three-dimensional model.
It's possible to be frustrated. You already assumed it commutes, right?
But they have to also be minimized simultaneously in the ground states.
I thought you assumed they all plus one eigenspace. Well, that's the something frustration free.
Yeah.
Sorry, can I ask you a quick question? When you say what phase does it matter is realized by stabilizer code? Or are you saying I want to characterize what the ground states of Hamiltonians of this form what's the relation to the ground state and the stabilizer code? That they're in the
Well, simply put, I'm just classifying all phases of matter whose Hamiltonian is in that form. That's my goal.
what does it mean to be realized by a stabilizer code?
Well, it's
There's a simple mapping between the stabilizer, between the code being the one eigenvalue of all stabilizers, and that code being the ground state, the ground space of a local Hamiltonian.
Is there a uniqueness or anything, or?
Yeah, it's just projection on the one eigenspace.
Oh, okay.
is that okay for you?
Yeah.
Thank you.
Sorry.
Since I'm assuming it's translation invariance, my Toric code will be defined as the square lattice, strict square lattice. It won't be an arbitrary graph. So as usual, each edge is associated with a single qubit, and there are two interaction terms. This is not plus sign, it's just a. So each blockhead is acted upon by this blockhead operator. And each vertex, there is a corresponding so-called star operator consists of sigma x, tensor product of sigma x. Any question for this notation? Should be clear. So let me first answer how many ground states are there. You will all know that on the torus there are 4, but let me explicitly calculate that. Like I told you before, on every the stabilizer code, there exists a Pauli operator that, that generates the operator algebra on the code space, which means all I have to do to figure out the number of ground states, I have to figure out what Pauli operator really acts on the code space. So suppose I just flip, well, I start with the arbitrary code vector, the ground state, and then suppose I act by sigma z at one edge. What is the energy of this state with respect to this Hamiltonian? All I have to do is to measure these operators, which means I apply some, well, P is one of the star or plaquette, and see what the eigenvalue it is. If P is a plaquette operator, it obviously commutes. So it will be like this, and by definition, P stabilizes the code state, which means this term does not pick up any energy. However, when P is a star operator that happens to act on this star, then there is a sigma x operator here that anti-commutes with P. In that case, I will pick a minus sign. Well, again, P will stabilize this. I'm left with a minus, which means I pick up energy, a unit energy from this Hamiltonian. Such a star operator appears at the two locations, here and there. Let me throw in more operators. Now, all you have to do is to find the terms in the Hamiltonian that anti-commutes with that operator. Well, it will appear here, here, and here. Well, well, operator here really actually commutes because it anti-commutes here and there, the even number of positions. But I can think of that as a combination of two minus signs that cancels. So I would like to just put the two dots and count the number of dots modulo 2. That's more convenient. Well, this is a simple calculation. I don't have to introduce any new notation for it. But for the sake of later generalization, let me do it algebraically. So I would like to actually express the positions of dots and operator in a nice way. So the input, so here you see, I throw in some operator to the ground state, and I obtain the positions of excitations, the positions of star or plaquette that is violated. So it means that the input is list of operator coordinates. Where should I put the operators? So it will be like, if I put this to be the origin, 0, 0, and this position is 1, 0, horizontal. And this operator is 1, 0, vertical. And that is 0, 1, vertical. So this is input data, operator position. And the output is the positions of dots. In this case, 2, 0, 1, 0. There are two dots at 1, 0. And 1, 1, 0, 1, 0, 2. That's my output. So my Hamiltonian functions like a program. I throw in coordinates and I obtain coordinates back. How would you program it in an efficient description? I don't want to work with the coordinates, so I introduced a trick to express those coordinates in the exponents. I mean, x to the 1, y to the 0, e of h. X to the 1, y 0, 0, y to the 1, e of v. And I just, well, this looks like a monomial, so I just put placeholder plus sign. It doesn't really mean anything. It just separates two monomials.
Sorry. I want to stop you just because I understand that you'll be using this a lot. So I didn't understand the h, v, and v in the locations of the z's. The second z in the middle has both h and v, no? So
This one?
yeah, for example, what's its coordinate?
This, well, I'm associating edge with the, so I'm associating the edge in this fashion. Vertical edge is always associated with the vertex in the south, and the horizontal edge I associate vertex on the left.
Okay, I see.
And well, same trick can be done here too. X square. Well, let me omit the 0 because it's gonna be obvious. X, y square. But actually, this plus sign makes sense if I compute everything modulo 2, because I told you that I put a virtual pair of black dots to express the overall plus sign, which originates from the cancellation of two minus signs. That is reflected here if I do the polynomial addition modulo 2. I just erase them. Now, my program accepts this polynomial with the special characters e, h, or ev, and outputs a single polynomial. Since my system is translation invariant, I can shift everything to arbitrary position. But here, translation means that I add certain numbers to all of the coordinates, which corresponds to multiplication of monomial of some exponents here, and distribute them. So
just to clarify your notation, these are locations of what?
Locations of sigma z operator that are applied onto a ground state.
Okay, so you're just using sigma z.
Yeah.
Okay.
Yeah. Generalization to sigma x will be easy. Just let me focus on sigma z. So the overall map is simply a matrix multiplication. You see, this single term is mapped to this polynomial. And the other term is mapped to this one. This one is mapped to here. Whenever I have EH, I multiply by 1 plus x. Whenever I have EV, I multiply by 1 plus y. And the rule applies here too. So if I if I express this as a column matrix by writing like x plus y. So upper row represents EH, and the lower row EV. And that's input, and all I have to do is multiply these two polynomials. Well, this is pure the usual matrix multiplication. Including sigma x, well, matrix gets a lot large because you have to express whether it is sigma x or sigma z. So I have a matrix. This explains all calculation I have done there. Whatever Pauli operator gave me, I expressed them using some column vector of this form with the positions encoded in the exponents. Multiply this matrix, the result will be the positions of excitations. Now, get back to the original question. what are the Pauli operators that act on the ground space? Those are precisely operators that does not create any excitation, because by definition it should map a ground state to another ground state, which means if I apply this map, it should result in a 0. Right. So I really compute the kernel of this matrix over the polynomial algebra. Well, subject to the boundary condition, like x to the L is really doing nothing, which means 1. And translation into y by L times is really 1. So, not all solutions of this kernel is going to work, because we have seen here, one logical operator can have many representatives. It could be expressed in this way or in that way. They are really the same operator. And by definition, these are commuting with one another, which means if I plug in Pauli operator that happens to be a term here to the epsilon matrix, I will automatically get 0. So I have to mod out those trivial solutions. And those trivial solutions also have a matrix representation. Can you see this? So it's not very difficult to see that the image of this matrix actually generates all trivial solutions of this. So the logical operator is really this. It has one-to-one correspondence with the non-trivial representative of the logical operator and then one element in this set. And now, so, yeah.
That's called sigma there now.
Yes, that's called sigma.
What do you mean with the image of this? I didn't get that.
So here input is a two-component vector because it's 4 by 2. So you apply all possible polynomials here and obtain a set of polynomials that is expressed in this way. And that forms the image. So I have transformed the representation of the Toric code using just 2 matrices. Well, in fact, the 2 matrices are not distinct ones. You can obtain one from the other one. And the formula is just a transposition followed by a simple row operation.
Do you work with the Laurent polynomial, or you convert y to the minus 1 into y to the L minus
Yeah, I should have said it's the Laurent polynomial precisely, but.
So, do you think something like that would also work for codes with higher dimensional units?
I'm going to that.
Okay.
Yeah. And this is non-zero only if you can actually see that this is only non-zero when you impose boundary conditions. Without this, actually, this object and that is the same. Let's see that. Well, this is actually direct sum of 2 block diagonal things, so let me just focus on this submatrix. So if I have suppose I multiply some polynomial by this matrix, and suppose I obtain 0 without boundary condition, then it means they are the same. I'm working modulo 2, so sign is never important. But, well, polynomial has a unique factorization, which means 1 plus x should divide b times 1 plus y. But 1 plus x does not divide 1 plus y. Therefore, it should divide b. Likewise, 1 plus y should divide a. And in turn, because of equality, you must have this relation. Then, well, my original variable becomes times c, which is indeed generated by this portion. So without boundary condition, this is really 0. What does that mean physically? It means this is essentially local indistinguishability, because if I have some operator that acts on the ground space, and suppose the operator is supported on some finite region, as long as it's finite and does not touch the boundary, it is expressed as some polynomial of finite degree, right? And if I plug in into the epsilon, I obtain the 0. I should obtain 0. But the calculation says that those operators are actually generated by this, which means it is generated by the terms in the Hamiltonian. And the terms in the Hamiltonian is by definition acts trivially on the ground space. So the logic goes, the conclusion is, whenever you have a finite operator that does not create any excitation, it is expressed in terms of trivial operators. There's no operator that can act non-trivial on the ground space. So having this object 0 without boundary condition implies local indistinguishability of ground states. Now, let's make an observation. In this calculation, I didn't really use any fact about 2 dimensions. All I needed is that 1 plus x does not divide 1 plus y and vice versa. So let me replace with arbitrary polynomial.
So I have a question. So the code is really sitting in that map, right? This
Yeah.
1 plus x plus y.
Yes.
That fully determines the code. But you're saying this is a general property. You're showing here explicitly.
Mhm.
But this fact that if you don't get the boundary, you have to get the boundary conditions in there in order for this to be non-zero, right? Yeah.
We just compute the first homology of the torus.
Mhm.
Right.
It's essentially the representation of cellular tessellation of the
Without
torus.
boundary condition, just says the first homology of the sphere is 0.
Correct.
But this is a representation in what?
Representation in...
Representation in...
It's not really representation of something more algebraic. It's just technically it's a representation of the translation group. But I don't think that interpretation helps anyway. So suppose I had an epsilon map with where the bar means that I replace every variable with its inverse. Well, that's a technical reason, but it works. And suppose I have just coprime 2 polynomials, then whatever I throw in, I will get locally indistinguishable ground states. And well, it doesn't have to be polynomials in 2 variables. It could be any variables, like you pointed out. This enables generalization to arbitrary dimensions. Number of spatial dimensions is equal to the number of variables.
I missed the argument about the local indistinguishability.
Okay.
Where do you get the local properties?
Local property is encoded in the fact that any local operator is represented by finite polynomial. It's not a series. The degree has to be some number. Indeed, without the condition, you can multiply like if you plug in, then you get 0. So let me choose a particular two polynomials. There is no particular reason that I chose something symmetric, but the calculation later becomes nicer when I chose this. Well, the only thing important here is that their GCD is 1. And using this, you can actually figure out what the Hamiltonian was. And the answer is the so-called cubic code. Well, physically, this is a crazy model. It has an 8-body interaction, and it has a very strong anisotropy. So I'm not very sure about the physical relevance of this model, but it's theoretically interesting to study. So I just changed the 1 plus x with the simple polynomial in the 3-dimensional model. What's special about this?
Question, the way you choose this G and F the bar is because of things have to commute, right? There has to be some constraints in there.
The spins live on the bonds?
Spins live on the site.
Sites, okay.
Uh-huh.
Like, for example, the ZZ, what does it mean?
So this is really a, this really a sigma z, where the coordinates are inserted or coordinated to this diagram. It's really a product of 8 Pauli matrices, and I means there's none. And similar for sigma x. Okay, so.
But so the dimensionality, if you want a high-dimensional code, you'd have to have a higher degree pool, that is, or no, higher number of
higher
variables.
Number of
Sorry,
variables.
yeah, number of variables, not degree. Yeah.
Did you just translate your code into this formula, or
No. Well, it went backwards. I observed this at the very last stage. So what's special about this? The strange thing happens in the excitation as well as on the ground state degeneracy, but let's focus on the excitation first. Well, precisely because the epsilon map here is designed to capture all aspects of excitations. I throw in Pauli operators, and epsilon tell me where the excitations are. So let's start with let's focus on this element only. And let's focus on the vector v, where vector is like something here and strictly 0 there. So I'm ignoring this g part. Suppose I start with 1, which means I introduce a single sigma z at the origin. Then epsilon v tells me that this is my excitation. Well, exponents represents the coordinates, so it means there's excitation at the origin, 1, and 1 at the 1 unit to the x direction. So there are four excitations arranged in this fashion. Well, since this is polynomial, so let me replace 1 with this f, or vary this. And what happens? What epsilon tells me I have to square it, but modulo 2, any coefficient 2 is equal to 0. So I just do the seemingly wrong calculation, which is only valid modulo 2. Well, that means the distance between excitations has been doubled. Right? Let me do one more step. Yeah, 3, 0 was 3, 2, f square, f. Now,
Sorry, you don't understand. What's s squared f?
literal polynomial, you just you plug in that expression.
Yes, okay, sure.
Yeah. Well, epsilon v2 is f times f square f, which is f to the 4. Well, 4 is the power of 2, so f2 to the 2. Well, this is you get another doubling of a separation between excitations. You can keep doing it. You just plug in Vn f to the 2 to the n minus 1 all the way to f. Then this will give us excitations that are separated by 2 to the n plus 1. But how does this operator look like?
So can you interpret your excitation as a tetrahedron?
Yeah, if you can. Yeah.
So that's the shape of the excitation.
So let's figure out this expression. First, well, f 1 is 1. F is times 1. F square f is
Every time, like the first one, you put in 1z error. Then you put in f, which is these errors on these sides, and then you see what you get.
well, yeah, I'm mixing two things, but the mixing is possible because I'm
Yeah,
using polynomial.
right.
There's no ambiguity there. So let's look at in terms of coordinates. This is a point, and whenever I multiply this, I distribute them in a certain way by distance 1. But at the next stage, each such configuration is copied 4 times that are separated by distance 2 away. And in the end, I will get some fractal. It's a convenient way to see, well, generate some self-similar structure, this particular combination here.
I'm sorry, you're trying to generate a structure with what properties? I'm not sure I understand what is it that you're doing.
So my original intention was to have a configuration where the excitations are arbitrarily far away. And this is one particular way of getting that configuration. And now I'm interested in what operator does the job.
So maybe it's a similar question, but if you can somehow describe your intuition to looking for co-prime polynomial, give you that already so much.
Well, I'm not sure if it is intuition, but you can actually generalize into it doesn't have to be 2 by 4 matrix. It can be T by some even number matrix.
But so something was probably guiding you in making these two.
Well, cube is not that important
The
because
structure of the stabilizers. Stabilizer generator. Somehow we
well, let's do the calculation first.
But this formalism came after you came came up with the code,
Yeah,
right? So
yeah.
you search for the code in a very different way. But,
Yeah, I did. Well, yeah, anyway, here in this particular example, it was possible to isolate a single excitation from the rest by arbitrary large distance, and the operator that creates that configuration has some self-similarity. But surprisingly, this is essentially the only way you can separate a single charge. Any isolated excitation always appears as a vertex of some fractal. This may not be a very trivial statement, and it's one of the theorem I have proved. Of course, you have to define what the fractal means here, but essentially, any isolated excitation, there exists some certain polynomial like f here, and when you combine the f in this way, then you are left with the target excitation left.
So your excitation has a symmetry, which is Z2 cross Z2. You survive to the fractal, right? You just scale this up. This with, you have a tetrahedron.
Mhm.
You have a Z2 rotation on the two axes. Where you do
Well, that statement does not require that symmetry.
But I'm saying your excitation have this symmetry.
Uh-huh.
Where you go as large as you want. It's always there.
This statement is true when the matrix is large. I mean, it doesn't have to be in this form, but if you remember the setting where the code Hamiltonian is translation invariant and written in terms of Pauli operators, this always holds. Yes.
So that would be the string onions in the torque. So anytime you want to push far away, you must have some footprint which behaves like this way.
Oh yeah. And in particular, the usual notion of string is a special case of fractal because line resembles itself. You know.
But I don't quite understand what you said. Whenever that matrix is large, you have this statement?
The fact that there are two rows reflects the fact that there are two types of interactions in the Hamiltonian, the star and blockhead. But in principle, you could have as many interactions as you like.
So how general is this? Can you achieve the same thing, not in 3D, but in a general?
It holds in arbitrary dimensions.
Okay,
as
so
long
the
as you
general
have-
graph,
No general graph, it's cubic lattice,
cubic lattice.
hypercubic lattice.
Okay.
So the translation group should be some product of integers.
I see.
Well, that's interesting. What happens in 2D if you just pick f equals 1 plus x?
Well, let's do the calculation.
Okay.
So when f is 1 plus x, then so this is a point to 2 points. Well, you can just expand it. It just So the number of term matters. If you have 2 terms in it, then the fractal it generates is a string. But if you have more than that, then it becomes something.
So if I pick f equals to 1 plus x plus y in 2 dimensions, then you get the 2-dimensional fractal.
Yes.
But what's the molecular entropy for that kind
So I think I'm over time already, but two-dimension is very special. You can introduce co-prime polynomial using two variables arbitrarily, but you can show that it is after certain local unitary transformation and some coarse grading, you will end up with the usual Toric code. That's a very special property of two dimensions.
Is it also related to the fact that we're using Z2
No. Well, this formalism straightforwardly generalized to the qubits with prime dimensions. So it has little to do with being you're using qubit, but really two dimensions matters.
So I have another question, but it's related to the talk that the read case. So if you have a condition, let's say I want a code where if I have an error with high weight beyond some number, that the syndrome has high weight scales with the weight of the error. Is that a condition that you can put into this?
No, I didn't put that condition.
No, I understand you didn't put a condition here, but can you put it into this formalism?
So
Because it depends on the, I want a code where the weight of, the code is such that if I have an error of weight k, and k is sufficiently large, that the syndrome also has weight k or scale.
Oh, luckily locally testable codes.
Yes.
Well, if you are stick with a lattice setting,
Degree of the polynomials.
if you are stick with a lattice, and if you consider family of codes parameterized by the system size, then that will not be achievable. Because, well, simply because in the lattice setting, well, you can just stack the stabilizers in the Hamiltonian such that it occupies certain non-trivial volume. And it will not cause any syndrome at all. Of course, it's not an error, but
No, it's an error.
but
Okay, yeah,
But it,
but then,
But you're only counting
Yeah.
with respect to error. I mean, if you can fact that you can somehow find an equivalence where this code has smaller weight, then you're okay. With respect to those.
So does the third system where you sit here in some phase status
classical is not possible. I don't know that it is impossible quantumly, but also you can take the dimension to be n or log n.
well, then something interesting might happen. The statement I made was just fixed dimension.
no, okay, so if you have to have dimensions,
Right.
yeah, but
Yeah.
I suppose this formula is very nice and compact, so maybe one can address this question.
Yeah, possibly.
I'm trying to understand what this physically means to say that an isolated excitation is the vertex of a fractal. So if I'm trying to have a certain separation between my excitations, does it mean I need to get the number of excitations I generate scales in some way with the separation?
Right. So usually without a point-like excitation to be attached to a string, that's the only picture we had. But the cubic code showed that it's not necessarily the case. But then natural question is, what else could it be? But this says that's pretty much all in the fixed dimensional setting. So if it is real fractal, then it is not that there is a potential between two charges. The charges are deconfined. However, in the process of making that configuration, you should go over some high energy state.
So you can still just get a pair of isolated charges.
Not a pair. Pair is not allowed.
Maybe 4 of them. So.
Yeah. And another statement that I want to, advertise is that three dimensions is also special because in 3 dimensions, 2 dimensions, all fractals are a string essentially. But in 3 dimensions, you must have certain fractal. Well, it can be some string-like, but like in the 40 Toric code, you don't really have any point-like ones. All you have loop-like ones, but that does not happen in 3 dimensions. comments I need to include here. Thank you.